now comes a very, very important concept which I want you to pay very close attention to. So if you were to remember, we have studied the ideal low pass filter. Ideal low pass filter is given by a dTft He of j omega equal to 1 for all frequencies less than omega c and equal to 0 otherwise. Okay, and we have sketched this, but let's sketch it again. This is a rectangular function which has a height of 1 and it goes from minus omega c to omega c. This is He of j omega. And we know that this system has got impulse response which is given by H of n equal to sine omega c n divided by pi n. Okay, let me take this particular, copy this. This is the sketch of the sinc function. This is how the impulse response looks like. Okay, some important properties to note. So there is symmetry, and it turns out to be even symmetry, which you can verify. H of n is equal to H of minus n. It is non-causal, okay, and it is of infinite duration. Infinite duration, non-causal, even symmetric signal is the impulse response that we have. Okay, now I want you to look at what He of j omega will be for this particular LTA system if I were to compute it using the discrete time Fourier transform. Summation n equal to minus infinity to infinity H of n e power minus j omega n. Okay, take the 0th term separately, take the plus 1 and minus 1 terms together. H of 1 will be e power minus j omega n. H of minus 1 will be e power j omega n, but this is the same as H of 1. So the combination of these two will be equal to 2 times H of 1 cosine omega n. Okay, and then you will have H2 e power minus j2 omega. So this should be j omega and j omega cosine omega, and this will be j2 minus j2 omega. H of minus 2 e power j2 omega. This combination is going to give me 2 times H2 cosine 2 omega and so on. Okay, and notice that He of j omega is fully real valued. It is not a complex valued quantity, real valued. Okay, this means that if I ask you to compute argument of He of j omega, you will come up with a value equal to 0 for all values of omega. Okay, so this He of j omega, which satisfies this property, is called a zero phase function. The phase is identically equal to 0 for all values of omega. Okay, very, very important type of function that you will find, and we can explain this a little bit more, or to generalize, you can look at any sequence with symmetry. Any sequence with symmetry. Okay, we can of course look at even symmetry, also look at odd symmetry. You will find that these sequences will be zero phase, which can satisfy zero phase. So for example, if I have a finite length sequence H0, H2, H1, H0, H1, H2, and this is my origin. Okay. Without even going through the process, I can say that argument of He of j omega in this case will be 0, will be a zero phase function. So some points to note about zero phase transfer functions. Zero phase transfer functions. Okay, they will be non-causal because they must have the symmetry. They will be non-causal and they will have the symmetry. They will have either even symmetry or odd symmetry. It doesn't matter. Both of them will lead to zero phase. And these linear and they can be finite or infinite duration. Finite or infinite duration. Finite or infinite duration. Okay, these are important properties or important things for us to keep in mind, and therefore we are then able to work with this transfer function. So for example, if this is the h of n, okay, h of n, then we can write down the expression which is given by He of j omega as H0 plus 2H1 cosine omega plus 2H2 cosine 2 omega. That is the expression for He. Now, an important thing for you to note is that if I gave you another sequence H1 of n, which is H2, let me call it as W of n. H2, H1, H0, H1, H2, but the origin is here. Okay, now We of j omega. We of j omega will be H2 plus H1 e power minus j omega H0 e power minus j2 omega plus H1 e power minus j3 omega plus H2 e power minus j4 omega. Okay, it looks like the symmetry, the zero phase property just got lost and there was no outcome. Not quite, because if you pull out e power minus j2 omega, then you can see what happens. You will get H0 plus 2 times H1 cosine omega plus 2 times H2 cosine 2 omega. So basically the same zero phase type of transfer function we got, but the phase term, so this is real, right? This is real valued. So the phase is completely in this term. So this is where the phase is. And so if I were to ask you what is the argument of We of j omega, then you will say it will be equal to minus j2 omega. Okay. So, minus 2 omega, minus 2 omega, minus 2 omega. So, this is a linear phase function, linear phase. Okay. So, if I have a even symmetry, then I will get zero phase. If I shift it in terms of time, then what I get is I will get linear phase. So this is a very, very important aspect because non-causal systems are not realizable. Okay, so LTI systems with zero phase are not realizable because they will require you to have non-causal. However, LTI systems with linear phase are definitely realizable. With linear phase are realizable, and you will still preserve a good relationship between the input and output phase. There is a linear variation. It is not zero variation, but it is a linear variation, and therefore from a group delay point of view, you will see constant group delay. There will not be any impact. So linear phase, LTI systems with linear phase are realizable. Okay, and this is also powerfully illustrated with the ideal low pass filter. Okay, so this is the ideal low pass filter. As we said, it is non-causal, it is doubly infinite, and it's a sinc function. Now, what we can do to implement a low pass filter is we can say that we will truncate this impulse response to some number of samples. Let us say that the number of samples from 0 to here is a number equal to ND. Okay, so basically from minus ND to plus ND, I have truncated my impulse response. So the realizable filter, H practical filter, that low pass filter that we can realize, is obtained by first of all introducing a delay of ND units of time, and then truncating it in terms of the total duration. So what does the practical filter look like? Sinc sine omega c n minus nd. I'm going to delay it because only a causal function can be realizable. So sine n omega n minus nd pi of n minus nd, and there's going to be a rectangular window which is of this duration. So this will be multiplied by u of n minus u of n minus 2 nd plus 1. Okay, so from 0 to minus nd to plus nd, 2 nd plus 1 is the length of the window. So n minus 2 nd plus 1. This is a practical realizable filter which we can then implement in any LTIs in a system. So you can see that, and this will have, by the way, it will have, this practical one will have, it will not have zero phase, but it will have linear phase. Why will it have linear phase? Because it has got the symmetry property that, and it is shifted. So the linear phase. And by what will be the linear phase? It will be minus omega nd. So basically the shift of minus nd will be the one that will be the linear phase, and with this we can achieve the LTI system. So what are we summarizing here? Zero phase is very important for us. They will be good for study. Because they are systems which will not have any phase response. We can only treat them in terms of their the real part of their frequency response. On the other hand, they are not realizable. If you want to make them realizable, you must delay them in time so that we get a causal system which we can then apply and we can then implement. So this is what is important for us in the context of the zero phase versus linear phase systems.